Okay, so we've got the third exercise sheet to look through. Based on a bit of a suggestion from people, I will actually maybe only go through ideas and hints for 1 or 2 bits of each question, and then actually genuinely you have something you can try at home and do yourself. So for example, in part A, I'll maybe show how to do, how to use the cross transformation formula for the θ3 function here, and then it's very similar on this side, and it's something for you to try at home. And since some of these things, like part B, where we're supposed to prove a particular identity, is just a very direct verification once you have all the modular forms set up in place, I will maybe leave that for you to try. So, okay, let's make a start. Let me get rid of the little annotation and copy that below just for reference. So the whole point of this part is to use the cross transformation formula to check these transformation properties. And I'll just quickly write down what that cross transformation formula is. And say for a sufficiently nice function, then we can take the sum from n equals -infinity to infinity of f of n shifted by some x, and relate it to similar sum n equals -infinity to infinity, some phase times the Fourier transform of f. Just for my reference later on, I write down what the Fourier transform is. So we want to use this, and I will use this to check this transformation property for θ3. It's sum of q to the n squared over 2 of all integers. So I'm going to take f of x to be the function e to the minus pi tx squared, and you can very directly do the calculation and check that the Fourier transform of that is given as e to the minus pi y squared over t over square root of t. So there's probably no point going through the details of that. It's just to make a substitution in the e to the minus something squared function, and then you get the standard sort of Gaussian thing in from -infinity to infinity. E to the minus x squared dx is root pi, and you can go from there. So now I want to substitute this into the cross transformation formula up here and see what it says. And in this case, I want to take x to be 0. And we will get on one side sum from -infinity to infinity of e to the minus pi n squared t. So this is just sum from -infinity to infinity of f of n plus 0. And on the other side with Fourier transform, it's going to be sum from -infinity to infinity e to the minus pi n squared over t all over square root of t. And so now I want to take particular point tau in the upper half plane, use that to get a sort of real value for t, and get an identity that holds on these things on some particular line, and then by analytic continuation get it to hold everywhere. So this is the starting point. This is holding for the t real. T greater than 0, just from the conditions necessary to make this work. So now if we set tau to be it or in other words, t is tau over I. Then tau is lying on the imaginary axis. And take as a t to be real number t greater than 0. And this tells us that plugging into what we got from the Poisson summation, e to the minus I pi tau n squared, sum from minus infinity to infinity, is going to be the square root of t in front, that's tau over I to the half, sum from minus infinity to infinity, e to the I pi n squared, substituted in with minus 1 over tau here. And then just by tweaking this a little bit, we can get it in exactly the form that the θ2 function appears. Sorry, the θ3 function. So then this side should just be θ3 of tau, and this side should be tau over I to the minus a half, θ3 of minus 1 over tau. And this is basically the identity we wanted to prove, but we've only proved it in the special case of tau lying on the imaginary axis. So if I just scroll up to the top again, was exactly that identity that's now just dropped out of the Poisson summation formula. But as I said, it's holding on the imaginary axis. But since everything's nice and holomorphic, we can say by analytic continuation, it's going to hold everywhere because it holds on some actual interval. So it's going to hold actually for all tau in the upper half plane. And that gives us the transformation property we wanted. Now you can do almost exactly the same thing for θ2 and θ4, except when you try to use the summation formula for, say, θ2, you end up getting something that looks like θ4 on the other side. And that's exactly the transformation property you want to prove there, relates θ2 transformed with minus 1 over tau to θ4. So it follows in exactly the same way. Now, the next part of the question is to show, actually from these transformation properties, that θ2, θ3, and θ4 are modular for gamma 2, and in fact, they're weight 2 modular forms. So if we recall, gamma 2 is generated by matrices 1, 2, 0, 1 and 1, 0, 2, 1, are generated freely. So to check these things are modular forms of weight 2 for gamma 2, we just need to check they transform correctly under these two generators. So the first one is just sending tau to tau plus 2. The second one, we're sending tau to tau over 2 tau plus 1. And it's going to be a bit nicer to rewrite that as minus 1 over minus 2 plus minus 1 over tau. And then we can see how the transformation properties we've proven can be used in this case. I'm maybe going to make that minus 2 minus 1 over tau like that. And then we see sort of as the first step, we are doing this minus 1 over tau transformation, then shifting by period of minus 2, and then transforming again under the minus 1 over tau. So about the first transformation tau going to tau plus 2, I'm going to say this is really just a direct check. The fact that q is e to the 2 pi I tau, and so sending tau to tau plus 2 is not going to change that. If I put a plus 2 there, there's going to be a case where you have a q to the half appearing somewhere, so you're still going to get just 2 pi I dropping out. And so since that's 1, it doesn't change the q series at all. So theta 2, theta 3, theta 4, they sort of trivially satisfy the periodicity. It's then slightly more interesting to check the transformation under this other generator. And again, I'll just indicate how that works for theta 3. Then the transformation for theta 2 and theta 4 is pretty much the same, but you have to take a little bit of care. So I want to look at theta 3 of tau transformed by that matrix. So theta 3 of this transformation, as I said. And then if let me just for reference copy this transformation property down again. We can see that we can write theta 3 of -1 over this thing as theta 3 of this thing with a factor, this thing over I to the power half, to the power minus a half. And then we can use the periodicity in theta 3 to get rid of the -2. So adding 2 or subtracting 2 will not change theta 3. And then we can apply this transformation again. So this is going to go to theta 3 of tau. Right, because I want power half there, because I've taken this over to the other side. So overall, once we unwind this transformation using the inversion thing twice, you get that the result is theta 3 of tau times this factor. Now just take the 4th power of everything. And then if you simplify all of this, it should come out to be 2 tau plus 1 squared, which is then exactly the factor c tau plus d for that matrix. And so that shows it satisfies the transformation property under 1021. And it's of weight 2. So indeed, that 4th power of theta 3 is modular form of weight 2 for gamma 2. And I said it's exactly the same story for theta 2 and theta 4, except the transformation property for theta 2 and theta 4 involves the other one at some point. So you will apply first the inversion and get a theta 2 going to a theta 4, do the periodicity thing, and then apply the inversion thing again and get theta 4 going to theta 2. So overall, you'll relate theta 2 to theta 2, and same story works as above.
So are there no modular forms into gamma 1, but there are for gamma 2?
Yeah.
Right.
So I mean, there are things that transform like modular forms for gamma 1, except they have this non-holomorphic bit. That's the Eisenstein series of weight 2 that Daniel was mentioned. Right. But yeah, there's no holomorphic things that transform like that. And I mean, you've got a dimension formula from the lecture course that you can check the modular forms of weight 2 for gamma 1 would have dimension 0, so there's nothing.
And is there like a formula for the dimension of the modular forms for the gamma 2?
Yeah, that was on the previous exercise sheet. Or at least an upper bound for it. And then actually with one of the exercises here, you will even show that bound is like strict, because you'll be able to find two generators that are algebraically independent that give you exactly that many things in dimension k.
Right.
So So this is more or less dealt with the first part of the question. Part B, as I kind of indicated at the start, is just a direct verification. The idea is that you know theta 2, theta 3, theta 4 are all modular of weight 2 for gamma 2. You know from the dimension formula that it has dimension at most 2, so there has to be some relation. And then you can just set up the linear algebra by writing down exactly what theta 2, theta 3, theta 4 look like, or what their fourth powers look like. So for example, you could compute that theta 2 is 2q to the 8 plus 2q to the 9 over 8 plus so on, and therefore theta 2 to the 4 is whatever it is, 16q to the half plus 64q to the 3 over 2 plus so on. And then just check that the linear algebra will say that the coefficients in such relation have to be exactly that. And then I don't know, maybe we take a brief look at the idea for part C. I can maybe leave. And I can maybe leave some bits of that as an exercise for you. So the idea with part C is that from the previous exercise sheet, we have the dimension bound as k over 2 plus 1. So we know that there were most k over 2 plus 1 generators. If we take any homogeneous polynomial in theta 2 to the 4 and theta 4 to the 4, I guess with I plus j being k over 2, then since there are exactly k over 2 plus 1 choices for I, you will get that there are from this potentially the right number of generators. But you still need to show that theta 2 to the 4 and theta 4 to the 4 are algebraically independent. So there aren't any relations that spoil this. But the idea to see this is if there was a relation, some polynomial p of x, y, complex coefficients, and you can assume the polynomial is homogeneous of degree n, because there are not going to be any relations between modular forms of different weights. Then we really have would have an identity over the form some complex coefficients times theta 2 to the 4i, theta 4 to the 4 times n minus I equal to 0. And since we know that theta 4 is not identically 0, that you can just write down from the definition up here what the Q expansion is and see it's not identically 0. We can divide through by it to get a relation of the following form, or we can divide through by theta 4 to the 4n to get a relation of the form theta 2 of theta 4 to the 4i equals 0, which tells us that theta 2 over theta 4 to the 4 is the root of some complex polynomial. In other words, theta 2 over theta 4 should be a constant. And then you can just check from the definitions from their Q series that that is just nonsense. And so there can't be any algebraic dependence between them. They're algebraically independent. Therefore, taking these powers, theta 2 to the I, theta 4 to the j, is enough to give you all of the elements that should be in the space of weight k modular forms for gamma 2, and therefore this has to be a basis for it. So every modular form for gamma 2 weight k has to be some homogeneous polynomial in these things. So I'm not sure whether part D is really particularly interesting for this audience. Maybe I should skip it, or at least leave it for you to think about at home and look instead at exercise 2. And then after that, I guess I'll just stop at that point. So with exercise 2, the idea is as follows. Paste image. Yes, from Daniel's lecture yesterday, we know that the theta function for some even unimodular lattice of dimension d is going to be a modular form of weight d over 2 for gamma 1. So, and we know how to write elements of this as polynomials in E4 and E6, something like that. So we can just try to write an expression for these two theta functions in terms of that and extract some properties of the coefficients from that. So this is going to tell us that the theta function for the E8 lattice should be modular of weight 4 for gamma 1. And we know this space is just multiples of the weight for Eisenstein series E4, which has a Q expansion that starts 1 plus, was it 240 Q plus blah, 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 is equal to 1 plus the sum of the cubes of the divisors of n going from 1 to infinity. And on this side, we know that there's obviously one vector of length 0, so it's going to start 1 plus something. And so the rational multiple of the Eisenstein series on this side, which is equal to this, has to be 1. So we just have the theta function of the E8 lattice is exactly E4. And then since we have an explicit formula for all of the coefficients of the E4 Eisenstein series, we can see the sums of the cubes of the divisors of a number are going to always be greater or equal to 1. We just immediately get that for every choice of n, there is going to be a vector of the appropriate length. As for the Leech lattice, things are a bit more complicated because this should be modular form of weight 12. And we know that this space has dimension 2, so we can take a basis for that to be the multiples of the E12 Eisenstein series plus multiples of this delta function. It's maybe the nicest way to do it in this case. I'm just going to write down here the explicit expression you should get, and it's something you can check at home by looking at the Q expansion of both sides and seeing how doing the linear algebra to find the coefficients. We know that the theta function has to be some multiple of E12 plus some multiple of delta, and you will get that A has to be 1 and B has to be minus 66520 over 691. Just looking at the definitions of both of these and what's known about the number of vectors of length 1 and length 2 in this thing. The point now is to show again that apart from the coefficient of Q, there should be the coefficient of all the high powers of Q should be strictly greater than 0. And so this we can look at the Q expansion of the Eisenstein series. We know that this is starting something like this, some over 11th powers of the divisors of n, Q to the n. In particular, this is going to be at least n to the power 11. There's always going to be a contribution of n to the 11 from something the 11th powers of the divisors. We just need to show that the coefficient you get from the delta function, coefficient of that was this Riemannian tau function, is not so big as to make n to the 11 minus whatever the appropriate multiples are here equal to 0. And the idea for this is to use the bound we proved from the first exercise sheet on the growth of the coefficients of a cusp form. So we showed that they grow like n to the power of weight over 2. And in fact had some kind of explicit coefficient in front based on a bound for the function on the fundamental domain. So asymptotically, you only need you know that the coefficients are going to therefore be positive. And you only need to check the first few coefficients for whatever few is. To see if any of them are 0 or non-zero, and then you will get the claim in the question. You should be able to prove something like an explicit bound of the form 600 times n to the 6 just from some rough working I did. So we had that from the solution to the exercise on the first sheet, we had something like e to the m times e to the 2 pi times n to the weight over 2 as the bound when you looked at the absolute value of the coefficients, where this was the absolute bound on whatever the cusp form was, so in this case delta, on the fundamental domain. And I think just by looking at the Q expansion in book form and assuming that the imaginary part is greater or equal to √3 over 2, so you're in the fundamental domain, you can show something like the delta is less than about 1.11. Do some rough calculations. You should only need to check up to n less than or equal to 4 in order to confirm all the coefficients are non-zero. And then you get the claim in the question. And that there were vectors of all lengths root 2n for n greater or equal to 2. But there were certainly some details there for you to check yourselves. And to be honest, that might be a good enough place to stop, since you can the ideas of how to solve most of the questions, and you have something to try at home. So if you really wanted, I could say you could try to do some work in groups now and have a look at exercise 3, but I'm happy to stop there.
Okay, so I see some dubious faces. Are there any doubts, anything that you would like to ask?
Maybe I'll just make a comment on this. But it's always a fun thing, because these numbers one of the things. So you can first of all the serial focus. These are exactly the dimensions where you have either associated or alternative relation options. This is actually where the relations of that. It's kind of making
So it means it's even harder to do anything.
But the funny thing is, extra is actually very simple compared to the result. Just the same numbers.
Yeah.
This is your
It means it's even more hopeless to work with other dimensions.
Well, it is also the list of dimensions where you expression has a lot of
Okay, so yeah, okay, I'm going to stop the recording.